Hello, everyone, and welcome to our first CPA Turkey seminar of year 2022-2023. So on this special day, we're flattered and pleasured to have Professor Serhat Ekin to incite us about the geothermal emission controls. Serhat Ekin is a professor of petroleum and natural gas engineering at the Middle East Technical University based in Ankara, where he had his bachelor, master's, and PhD degree in petroleum and natural gas engineering. He has served on the facility since 1998 prior to joining the Middle East Technical University. Dr. Akin was a postdoctoral researcher in Petroleum Engineering Department, Stanford University between the 1997 and 1998. He was a Bullenstein visiting professor in Petroleum and Natural Gas Engineering Department. Dr. Akin has published more than 150 technical articles, reports, and conferences proceeding papers. Dr. Akin is actively involved in Turkish geothermal industry. He has helped in develop more than 700 megawatts electrical geothermal power capacity as a geothermal investment advisor to leading geothermal power companies and banks. His research interests include reservoir engineering, EOR, especially thermal, geothermal, reservoir simulations, tracers, and well test analysis. He received the Society of Petroleum Engineers Outstanding Technical Editor Award in 2001, 2002, 2004, 2014, and 2019. He also received Professor Dr. Tarek Somer Award in 2004 and the Middle East Technical University Academic Achievement Award between 2001 and 2018. He was an associated editor of the SPE Reservoir Evaluation and Engineering between 2007 and 2013. He is currently an editorial board member in Computers and Geosciences. Dr. Akin served in several CPA communities, including Education and Accreditation, Star Award, and International Facility Award communities. Furthermore, if any of our participants has any question, they may ask them in the chat side, and we'll forward them later to our professor. So, Professor Serhat Ekin, the stage is yours.
Thank you.
You're welcome.
Greetings. So my talk topic today is geothermal emission control, and I will be focusing on Turkey showcase. So let me start with a brief background of the project. Since 2007, gas emissions at Hellsheiði geothermal power plant in Iceland are significantly reduced through the CarbFix project. In this particular project, essentially the produced gases are injected back into the basaltic reservoir. So the pilot scale capture and injection commenced in 2011, and this has been expanded to industrial scale since 2014. Essentially, the carbon dioxide and hydrogen sulfide is captured using a scrubbing unit, and that only uses water and electricity. And then the captured gases are injected into the brine, which is dissolved prior to injection, of course, and then into the geothermal reservoir. And essentially, we observed that it is essentially going through what we call a rapid mineralization. Currently, about 1/3 of the carbon dioxide and 2/3 of the hydrogen sulfide are captured in this process. Essentially, this has proved that the carbon dioxide that is produced through the geothermal power plants is essentially can be re-injected back into the basaltic reservoir. So the project of the GECO aims to improve the efficiency of this pre-existing gas capture and injection infrastructure at Hellsheiði, and then turn captured carbon dioxide into value stream at Hellsheiði and commence pilot scale capture and injection at Nesyalavir power plants. So essentially, as part of the GECO, we aim to expand this process to different type of geothermal reservoirs, and the particular demo sites that have been established are, apart from the Hellsheiði and Nesyalavir power plants in Iceland, Hıvaragerdi and Kızıldere and Bokum Mule reservoirs are going to be used as demo sites. Essentially, at the beginning, a reservoir field Castelnuovo in Italy has been proposed, but then again, due to some permits problems, this has been moved to Iceland location again. Essentially, the total idea right here is to lower emissions generated from geothermal power generation. For those who are not aware of the scale of the emissions, the carbon dioxide emissions generated in Turkish geothermal power plants are sort of quite high, reaching to 1,200 kilograms per kilowatt. So in this particular project, we have partnered with several different companies, research institutions, universities. There are 5 industrial, 13 research and technology development partners located in France, Italy, Spain, Norway, Turkey, Germany, United Kingdom, and Iceland. From Turkey, we are partnering with Zorlu Geothermal, and essentially we will be demonstrating this carbon dioxide re-injection process in Kızıldere Reservoir. For those who are not familiar with the Kızıldere geothermal field, it's Turkey's first and highest potential geothermal field explored for energy generation. It's a high temperature metamorphic reservoir situated in the Denizli province, and it consists of 3 different power plants, both of them being different type of flash and hybrid power plants. The first one has been commissioned in 1984. Then an 80 megawatt capacity power plant was commissioned in 2013, and the remaining 165 megawatt power plants are operational since March 2018. Typically, 1/3 of the discharged non-condensable gases from Kızıldere 2 is sent to a carbon dioxide facility named Lindegas. Lindegas processes the carbon dioxide for commercial activities, like the sodas you're drinking, like Coke and other stuff. Of course, essentially the aim of this project is to further reduce the emissions so that we will have a greener geothermal power production, and yet at the same time maintaining the sustainability of the reservoir production. Okay, so let's simply talk about how we're going to achieve this. So here the idea is use a mixture of water and non-condensable gas that we will be injecting at the surface through the casing. So what we will be doing is that basically it will be injected from this particular injection well right over here. And we are hoping that as we inject this particular NCG back into the reservoir, it will be mineralize the whole thing over here, creating some carbonate minerals. I will be later talking about what sort of minerals we are expecting to precipitate as through the injection. As you see over here, we have a couple of neighbor production wells, and those, of course, will be subject to increased carbon dioxide injection. And through the project, we will be also monitoring the content of the produced carbon dioxide here at the production wells. And plus, we will be monitoring the surface CO2 soil flux. So this is what we call a conceptual model of the whole process. And we will see what sort of minerals we will precipitate through modeling. So we have conducted several different levels of modeling stuff. We have created a geological model, a conceptual model, and we have also developed a couple of reservoir simulation models. Apart from the soil CO2 flux, we are sampling shallow water wells, which are used for irrigation purposes, and we will be also conducting a tracer test where we will be injecting naphthalene sulfonate together with the carbon dioxide injection over here to trace where the carbon dioxide will be traveling, either to the production wells or at some different location in the reservoir. So prior to doing anything, we started with injection design. So on the right-hand side, you see a Google image where we have the power plant at the left-hand side over here, and this yellow line shows us the path of the pipeline that will be carrying the carbon dioxide with which is dissolved in the brine. This red dot right over here shows you the injection well location. And what we have done is we have created some simulation models. These are Welber models. We have used PipeSim and Olga. PipeSim is a steady state model, whereas Olga is a transient model. And we have simulated the injection process from the start of this particular location to the injection well and at the bottom hole conditions. So this one is showing essentially a couple of sensitivity analysis we have carried out for different water injection rates and different gas injection rates. And as you see, what happens right over here as the injected brine amount increases together with the gas, we observe an increased flowing pressure. So meaning that we would require additional pumping on compressor efficiency power, so that we would be pumping these things over here. Another thing is that it will be affecting the injected water as well as the system goes towards the bottom of location. These are conducted using what we call the PipeSim software. And essentially over here, we have studied the flow regime as the injection commences from the power plant location to the bottom of the well, indicated at this right-hand side of the plots right here. So over here, for a couple of sensitivity runs, we have seen that at the locations where we are between the power plant and injection well, we see intermittent flow regime, and then we see some slug flow for differing injection of carbon dioxide values. And at certain locations, we also observe bubble flow. Now, the importance of this thing is that basically at certain locations, we have some pipelines that are moving like an omega, and essentially the reason why omega is present in this section is that for allowing vehicles to pass through the roads that are present in the field. So at these locations, we don't want problematic high pressured some carbon dioxide slugs, and essentially we will be observing if we have higher injection rates at certain locations. And another thing is that if we further continue with upstream locations here, as we decrease the injection temperature, over here we will see a less and less bubble flow. So that is particularly important. Meaning that if we just directly mix the NCG or carbon dioxide into the re-injection water, it will be somewhat problematic compared to a case where we will have a colder water injection. Okay, so that's why we have opted to use colder water that could be used for injection. Once we have modeled and obtained these parameters, we have extended our research into modeling. And over here, the modeling consists of, as I mentioned, geological modeling and some large-scale computer models where we have full-scale field model right here, as you see on the top. But essentially, solving for such models or using such models is sort of problematic because of the runtime, especially when you have reactive transport, and if you are using advanced programs like TOF React, you will have some problems in terms of convergence. Essentially, if we use such a model where we have several thousands of grid blocks, due to the presence of the NCGs and due to the reactive transport equations, we will have certain convergence problems. And that's why we have opted to use a sector model where we will have this pilot injection well and plus the surrounding neighbor production wells only. So this is a much detailed, much smaller model, and this model can be easily used to model this transport and essentially the geothermal or geochemical interactions that will occur as we proceed with the injection. So the problem right over here is that if we extract such a small sector model from a large field model, essentially you have to implement some boundary conditions at the edges of the reservoir. And then, of course, the rest would be right over here. The fluid carbon dioxide injection mixture will be injected for 6 months long. And essentially, we will be, of course, interested in the long-term effects of the whole thing. We have a very detailed geological model, as you see right over here. This model is created in a software called Petrosim, which is coupled with TUF. And we have implemented all geological features and all wells that are used for injection monitoring and other stuff right here. As I mentioned, we have extracted a sector model from this large-scale field model, and the field model, even though it has some permeability values, porosity values, and other stuff that are present inside that is used to populate it, has to be refined so that this sector model can be used. What we have done is we have used some analogy, essentially, that we could use from outcrop rocks that are present from a marble location that we have obtained. And we used some image analysis techniques, and we have also implemented some modulus data and sensitivity analysis of temperature and pressures carried out for this sector model. And then what we have done is that essentially we have carried out what we call a natural state model. In this natural state model, the pressures and temperatures that you record prior to production of each of these wells should be nicely matched with the software. So what we do is that we essentially run the sector model for several thousand years, and we try to see whether the pressure, temperature, and the carbon dioxide will reach equilibrium at a certain point in time. And of course, at some point, we check the pressures and see whether they are in accord with the measured values as a function of depth, of course. And yet at the same time, we also check the temperatures here. And likewise, we repeat the same thing for the carbon dioxide. Since carbon dioxide is only measured at the well top, essentially for production, we only use point values of carbon dioxide measurements. So once we are satisfied with a match, we then proceed with what we call the reactive transport. So here, compared to original Carpix projects carried out in basaltic Icelandic geothermal reservoir, the mineralization process of carbon dioxide in the schist and marble reservoirs of the Kızıldere field will be limited, basically because of the initial high carbon dioxide mass fraction. So here we are sort of injecting a carbon dioxide mixture that is much less than the carbon dioxide that is present in the reservoir. So meaning that the reservoir minerals are already equilibrated with large amounts of carbon dioxide, and that's why the injected carbon dioxide does not go any significant process, any mineralization process right over here. So in contrast, only small amounts of calcite dissolves in the reservoir as the injection goes on, as you see, for several years. We have also checked out other minerals, like, several things are also considered, like pH, aqueous species such as calcium, magnesium, and iron. And we have also checked dissolved inorganic carbon as well. So over here, we created out some sensitivity runs so that we would be getting logical answers as a result of this particular reactive transport model. We would be also tracing the injected carbon dioxide. We have created some simulation models again using the same sector model, and we have carried out some sensitivity runs in order to see effects of differing fracture porosities, differing amounts of fracture and fault storativities that are present over here. And essentially over here you see we are not expecting quick breakthroughs. And this one, even though shows in January 22, you can shift it to later times, but essentially the tracer will be the major part of the tracer will be observed after several months. I mean, like this one, in the highest one has been observed in KD25B, and then 2A, and then 83, and so on. So essentially, if the fracture porosity is less, we will see quicker breakthrough and quicker mean arrival times, and that will potentially affect the results of the carbon dioxide injection as well. So how it's going to be the implementation? As I mentioned, mixing the NCG, which is mainly consisting of carbon dioxide in colder water, is advantageous. So if we directly mix this NCG in the reinjection line, which is approximately at 120 degrees or somewhat less, it will be disadvantageous. And that's why we will be mixing the NCG prior to injection in a water which we collect from a bypass pond. Okay, so most of the geothermal power plants in Turkey has a bypass pond. So in case of some sort of emergency or some problem, what you do is you just bypass the power plant and just move the brine, produced brine, to the pond. And the temperature of the pond is somewhat lower compared to the reinjection water, right? So that's why we will have an increased solubility of the NCG inside this colder brine that has been already produced. So what we are going to do is we're going to take the NCG, we will be capturing the NCG without doing anything, and then we will be passing through a shell and tube, so that we will be cooling it to a certain temperature, like 35 degrees, and then we will use a compressor, and then we will mix it with this pond water, which is approximately at 30 degrees. Of course, this will change seasonally, and then we will use a compressor over here, and then mix it with the reinjection line over here. And since this reinjection line is already at a certain pressure, it will be carried together with the brine, and then we will be injecting it at the well top. Okay, so we have checked the following composition. This is from the effluent water. This is the composition that we have obtained at the pond water, bypass pond water, and we have calculated the mixture 1 and mixture 2. These are two different locations at certain positions in the injection system. And we know how much calcium chloride, iron, and other stuff over here will be changing prior to injection. Okay, so this is quite important, because in order to model the whole process accurately, we need to have an idea about the injected composition. So this one, of course, by composition I mean the mineral composition. And what we do is that, essentially we have observed several minerals that we have grouped under 4 different parts, and that we will be checking out each of these minerals prior to injection and after injection. Okay, so basically these are before and after carbon dioxide injection. So, for example, these group of minerals will not be seen after injection, but some of these minerals will be seen before and after injection as well. So, depending on these, we have created a model. We have created and calibrated this model using a simulator, what we call React, and then we modeled the injection over here. So what we have seen is that if we mix it with the background water, I mean the water or the brine that we collect from the bypass pond, we will be charging the injection water as you see right over here. So basically, we have identified each of these minerals, and we will be checking the values, of course, later on at the monitoring stage. By sampling the brines that we produce from the production wells and, of course, at the injection well as well. So we would be, continuously monitoring these values, and then we will be changing the injected amounts in our, simulation model. Apart from that, we have conducted several monitoring studies. One of the certain things that should be considered in injection is that basically we have to find out whether all of the injected carbon dioxide will be traveling to the production wells, as you see right over here. And that's why we have decided to monitor the soil CO2 flux. Okay, we have focused ourselves to some fault locations, as indicated by these red lines over here. And we have also focused around the injection well. And we have also selected some random locations that we believe that could be connected the injection well to production wells. So essentially, we used a Lycor 81000 model soil CO2 flux meter to measure the carbon dioxide flux at certain locations. So you can see the background, geothermal power plant located in Kızıldere. And this device, this is a portable device, by the way, we move it at these yellow sampling locations, and we try to find out what's going to happen, whether we will be having some CO2 leakage around the well, or whether we will have some CO2 increase at the fault locations, as you see right here. So these are the results that we have obtained prior to pandemic. We have, carried out several different seasonal measurements, as you see right over here. The lighter greens over here indicate some higher, values, as you see. So these are probably some, vent locations. These are the, heights near the horse section of the graben. We don't have anything at all at the center, you see. We only have increased activity at certain times, and these are, of course, maybe related to some irrigational activities or even some different things, later on. We will be monitoring some certain satellite data to see whether these are related to irrigation or not. So this is the result that we have obtained. So over here, this is the soil CO2 flux measurement. And we certainly see some sort of trend, the seasonal trend is obvious right over here. Essentially, we will have, negative relation with humidity and positive relation with the soil temperature over here. So, as the soil temperature increases, as you see, we will have a carbon dioxide flux increase as well. But on the other hand, we will have a negative effect of humidity. We are also monitoring shallow water wells. These blue dots right over here represent the locations of shallow groundwater wells. We are continuously monitoring these values so that we will be aware whenever any unexpected carbon dioxide movement will occur over here. We should see some differences in, for example, bicarbonate, values, and depending on the values, we will be deciding whether the carbon dioxide have reached to that particular well location as well. These are some sample analysis that we have carried out. As I mentioned, we are continuously collecting samples, and these actually show that, for example, the sample point 4, that well is actually quite close to Kızıldere production wells, as you see right over here. So actually these 3 wells are representing the shallow waters. So essentially, if we see any difference, from these, mineral compositional differences, we will be saying that, okay, this has affected this particular well and so on. So this concludes my presentation. Thank you for listening to me. Here are a list of people that currently collaborating the project, and with the past collaborators as well. So this project is funded by the European Union's Horizon 2020 Research and Innovation Program under grant agreement number 818169. Thank you. If you have any questions, please feel free to ask. Thank you.
Thank you very much, Serhat, Professor Serhat, for the informative and insightful presentation. And we thank you so much for accepting our invitation for today. And actually, I have a couple of questions that I have prepared to ask you, if you may. The first question is, what are the difficulties that you have faced during the project, and what kind of risks is imposed during the project? The second question is, what kind of mechanical wellbore failures have you encountered or have you faced? Mm-hmm. My third question actually is, do you expect any gas leakage through the permeable faults during the project?
So, regarding the difficulties, essentially modeling is quite challenging right here, basically because whenever you are, trying to model a reactive transport process, you have to have a database. This database should include all of the minerals that you have right over here, with the activation energy and other parameters should be properly represented. And most of the time, these data come from some experimental measurements. Unfortunately, we don't have many experimental measurements, especially in the metamorphic rocks that we have, the schist reservoirs, the marble reservoirs. And that was, one of the biggest challenges that we had. And apart from that, of course, the other challenges that we face is usually bureaucratic problems that we have at the Middle East Technical University. And of course, the COVID-19 pandemic has affected our measurements. We couldn't, visit the, field and the power plants for a long while. And then the project had to be postponed for like 6-7 months. The injection would have commenced last year actually, but now we will be injecting the carbon dioxide in June possibly, hopefully. Regarding the mechanical failures, most of the geothermal wells have some sort of cementing problems, especially at certain locations where you have groundwater movement, for example. And at certain locations, if you don't have, a nice cement bond, you may have some casing failures at certain locations. And that's one of the reasons why we are actually looking at near wellbore, whether this injected carbon dioxide will be leaking to the surface or not. So what could have happened is that, once you inject it at, this particular well, the carbon dioxide may move through, near the casing location to the surface if you don't have, proper cementing right here. Apart from that, we could face some movement of carbon dioxide at the fault sections. Because as you see, when you inject carbon dioxide, some of the injected carbon dioxide together with the brine will move to the production wells, but some of the carbon dioxide will not be able to enter because of the storativity limitations into those faults. And that will, reach to a different, perhaps, section of the reservoir. And from that section, maybe they could move to the fault sections. And I don't know whether you have been to a geothermal reservoir in Kızıldere before. The Kızıldere field has fumaroles at the horse section of the field, and you can actually see some steam coming out of these fumaroles especially during the winter time when the weather is cold. So these locations are possible targets for carbon dioxide movement. And of course, due to the nature of these fumaroles, the faults that feed these fumaroles might contain the injected carbon dioxide.
Thank you so much, Professor Serhat. So my last question is, do you expect any two-phase flow in the reservoir due to the re-injection of gas due to the decline pressure at the reservoir?
No, there will not be any. There will not be any two-phase flow. The moment, as you see, we have simulated the injected carbon dioxide using some well-bore simulators. All of the injected carbon dioxide will be dissolved in the brine. Of course, if you are not injecting huge amounts, that's the only thing that could happen. I mean, if you inject more than 20 tons, 40 tons, 50 tons perhaps, of course there might be some a gas pocket or like a gas plume that may develop around the injection well. So over here, we don't expect any two-phase flow. And of course, the idea is to re-inject back into the reservoir so that we will have reduced emissions. And plus, we will be using the carbon dioxide's partial pressure to keep the actual reservoir pressure at a certain level. So this will help us to sustainability. Essentially, if we keep on releasing the carbon dioxide and other gases to the atmosphere, we will have reduced amounts, and that will not be assisting us in keeping the reservoir pressure.
Thank you so much, Professor Serhat. Actually, I see a question in the chat side. If you have any time, I can ask it. Yeah, thank you very much. So the question came from Caner Akçay. He said, thank you very much, Serhat Hocam, for your valuable webinar. Mm-hmm. And I will ask a general question. Can we continue to use fossil fuels, or must humankind adapt and find better, more sustainable ways to produce energy? Which ones and how fast? Ideas, and thank you again.
I mean, of course, one of the challenges currently we face in the oil and gas industry is that, we haven't introduced any new ideas regarding the, production methods. We are not able to increase the recovery factors. And of course, the oil and gas industry is also facing the, emission problems as well. So if you think about the carbon dioxide footprint of such operations, re-injecting the produced gas back into the reservoir has a large impact in terms of reducing this carbon footprint. So essentially, as one of the Spanish research institutes that are part of the GECO consortium is studying this particular approach, and we are calculating the carbon footprint of these injection processes. So the idea here is zero emission, and I'm hoping that these methods would also be used in the oil and gas industry as well. So if you're familiar with the Turkish Batırama field, essentially, they have this injection process going on from the nearby Dodan carbon dioxide reservoir to the Batırama field, right? So essentially, they have implemented some cycling stations so that they will be capturing the produced carbon dioxide, and using these stations, they are re-injecting the gas back into the reservoir. I'm expecting that these will be gaining momentum. For example, like the cement industry, these are huge emission providers. They have to somehow collaborate with oil and gas industry, as well as perhaps the geothermal industry as well, so that they would be re-injecting the these gases into the reservoir.
Thank you very much, Professor. Actually, another question came. We thank you a lot for your valuable time, for giving it to us. So,
Sure.
if I may ask it, thank you.
Sure.
The question came from Hassan Can Turunç. He says, thanks for the informative presentation, Hojam. I have just wondered about the optimization of your production amount regarding the well spacing according to the reservoir conditions in Kızıldere.
Yeah, I mean, the injection process is pretty much standard. Essentially, we have to match the injected brine amount at the wellhead. Okay, so these change from field to field, location to location, and it depends on the reservoir pressure. So we use some pumps to get the brine from the power plant and inject it at the wellheads. So some of them operate at 30 bars, some of them operate at 45 bars. It depends on the reservoir, the depth of the well, and as well as the location, depending on how many neighbor production wells are present. So as a function of spacing between the injection well and production well, and if the permeability is quite high, you will have less injection pressures. But on the other hand, if the storativity of the reservoir is quite small, and that we have a large spacing between the injection well and production well, we may have much higher injection pressures. But currently it's close to 30-35 bars, and we don't expect this to be more than that currently.
Thank you so much, Professor. So I don't think any more question has came. Thank you so much, Professor, for giving us your valuable time, for accepting our invitation, and for the insightful and informative presentation. We also thank our participants, and we hope to see you all soon in our upcoming events and webinars. Thank you so much, Professor, again.
Thank you, and
I
bye-bye.
will see you soon. Bye-bye.
Have a nice day. Bye-bye.